In this lesson, we introduce the idea of a number system. We will see how a small set of symbols can be used to represent quantities, and how the position of a symbol can change its value. People have always needed ways to count things. They needed to count possessions, time, trades, animals, food, and many other quantities. At first, this could be done with simple marks. For example, 1 mark could represent 1 object. 2 marks could represent 2 objects, and so on. But as quantities become larger, this becomes inconvenient. Writing 1 mark for every object works for small numbers, but it does not scale well. Imagine writing 100 marks for 100 objects. Instead of creating a new symbol for every possible quantity, we can use a small set of symbols and combine them in a structured way. Let's build a simple number system. Suppose we want to count pencils on a desk. We will use only 4 symbols. These symbols represent 0 pencils, 1 pencil, 2 pencils, and 3 pencils. So if there are no pencils, we will use the first symbol. If there is 1 pencil, we will use the second symbol. If there are 2 pencils, we will use the third symbol. If there are 3 pencils, we will use the fourth symbol. Now suppose we find 1 more pencil. We now have 4 pencils. There is no single symbol for 4 pencils in our system, because the symbols only represent 0, 1, 2, and 3 pencils. So instead of creating a new symbol, we combine the symbols we already have. We write 1 symbol for 1, followed by the symbol for 0. This gives us a 2-symbol representation. The first symbol represents 1 group of 4 pencils. The second symbol represents no extra pencils. So together, the representation means 4 pencils. Let's try to interpret what the position of the symbol actually means. The symbol on the right tells us how many individual pencils we have. A symbol 1 placed to the left tells us how many groups of 4 pencils we have. This is called positional notation. Positional notation means that the position of the symbol helps determine its value. Now let's continue counting. 5 pencils are represented as 1 group of 4 and 1 extra pencil. 6 pencils are represented as 1 group of 4 and 2 extra pencils. 7 pencils are represented as 1 group of 4 and 3 extra pencils. After that, we need 2 groups of 4. 8 pencils are represented as 2 groups of 4 and no extra pencils. 9 pencils are represented as 2 groups of 4 and 1 extra pencil. 10 pencils are represented as 2 groups of 4 and 2 extra pencils. 11 pencils are represented as 2 groups of 4 and 3 extra pencils. And the pattern continues. Once the rightmost position has gone through all 4 possible symbols, the position to the left increases. This is similar to ordinary base 10 counting. In base 10, after 9, we move to 10, which is 1, 0, a 2-symbol representation. The 1 in 10 means 1 group of 10, and the 0 means no extra ones. In this pencil system, after the symbol for 3, we move to 1, 0. But here, 1, 0 means 1 group of 4 and 0 extra ones. This system is called base 4 because it uses 4 symbols. The base tells us how many symbols are available before we move to the next position. Here, the base is 4 because we have 4 symbols. Suppose we have the following symbol sequence. The positions are powers of the base. The rightmost position represents 4 to the power of 0. Since 4 to the power of 0 is equals to 1, the rightmost position counts individual pencils. The next position, to the left, represents 4 to the power of 1. Since 4 to the power of 1 is equal to 4, that position counts groups of 4 pencils. The next position represents 4 to the power of 2. Since 4 to the power of 2 is equals to 16, that position counts groups of 16 pencils. This symbol is in the 4 squared position. This symbol is in the 4 to the power of 1 position, and this symbol is in the 4 to the power of 0 position. So the number of pencils that this set of symbols represents can be calculated by this equation. The reason why this works is that each position represents a different size of group. The rightmost position counts single objects. Each move to the left creates a larger group by multiplying by the base. So in base 4, the positions count ones, groups of 4, groups of 16, and so on. The symbols tell us how many groups of each size we have. When we read the whole sequence, we are adding together all of these groups to represent a single quantity. This is why a small set of symbols can represent very large quantities. This approach prevents us from having to invent a new symbol for every quantity we need, but rather we can use the position to reuse the same set of symbols in larger and larger groups. Once those groups are counted together as ordinary base 10 quantities, we get the total number of objects being represented.